Alrighty, let's go ahead and get started with some practice with our fun solution stuff. We're going to do a couple of problems, then we'll talk about colloids afterwards. So, the whole point of doing a lot of the solution stuff that we've talked about with those colligative properties is to find out molar mass. That's kind of like the prime use of it. Often this is a lab that we would do in person, but of course that's not something we can do right now. The reason for this is molar mass is not something we can easily measure because we can't measure moles directly. We can measure all sorts of various other parameters that could give us moles if we were to calculate. Like if we knew what the substance was and its molar mass and we had grams, we could find moles. Or if we knew its concentration and a particular volume, we'd be able to calculate moles that way. Or for like gases, we could have any of those pressure, volume, and temperature to figure out the moles. But the easiest one, the mass, if we don't know the molar mass, we can't find out what the moles is. So we use other ways to figure out moles that can then help us to figure out the molar mass. And a lot of that, again, experimentally is from colligative properties. So here's an example. Here is some beta carotene. And we're going to dissolve that in, some solution, maybe benzene or something. We're going to throw that in. So let's say we dissolve 7.68 milligrams of this stuff. I don't know how to spell benzene. Aha. There we go. Let's say that our temperature is 25 degrees Celsius. And we were able to measure an osmotic pressure of 26.57 millimeters of mercury. So these are all things we can measure, right? We can measure milligrams. We would take out a balance or a scale, and we'd be able to measure that. We can measure out a volume. Let's go ahead and say this is actually of solution instead of benzene. Technically, this will be a little easier. The temperature, of course, we would use a thermometer. And then for osmotic pressure, we would probably use some sort of electronic pressure measuring device. Don't quite know what that would look like, but it is something we could measure. There are instruments to measure osmotic pressure. Or if we wanted to do like if we were using the boiling point stuff, we would be able to know that as well just by measuring the temperature. All right, so all of these stuff can be measured directly, physically, easy, no problem. And so let's try and figure out what the molar mass is of this beta carotene. So, how the heck are we going to do this? Probably the first thing we should do is take a look at our formula for osmotic pressure. That is the osmotic pressure. That's what's been measured as the osmotic pressure. So capital Pi is that's what it stands for. Cool. Remember that osmotic pressure has the following formula, right? We're going to see that we have 4 components of this. We have 3 of them perhaps that we know already. We know the temperature. We have R, of course, that's our gas constant. And because this is going to be, beta carotene is not an ionic solid. We know that because, hold on, I'm maybe about to sneeze. No. It's the worst feeling. Because it's not an ion, how do we know it's not an ionic compound? Look at the name. If it were named, like potassium fluoride or something, we know how ionic compounds are named. So this is just going to have an I of 1 because it's a regular plain old molecular solid. So, because it's not ionic. Plus, if it's in benzene anyway, benzene is a non-polar solvent, so we're not going to have ions in either case. So, we know all of these three things, and we know our osmotic pressure as well, right? We have the value for that. So, we're going to be able to calculate our molarity. Remember that molarity is going to be moles per liter. And so we can kind of just fill in things and, see what we get out. If in chemistry you have no idea what to do for a problem, throw in some equations perhaps and see what values you do have and try and calculate something, right? That's always what we do. So if we go ahead and just solve this equation for molarity, it's going to be osmotic pressure over IRT. And so, if we think about this, can we use this stuff directly? Remember that the units of R we know molarity is moles per liter, right? So we're okay with those two. But for the other two units, we're going to need atmospheres and Kelvin, right? However, we do not have those right now, so we can't use our formula right away. I'm just going to get rid of the formula in that case. In order to figure that out, let's go ahead and convert our pressure into atmospheres. What's the conversion factor for millimeters of mercury? Do we remember this from chapter 10? Trying to remember. Gas laws, remember? It is 760, if we recall. Yep, exactly. So if we go ahead and do this, 26.57 divided by 760, we get, this is 0.03496 atmospheres. Technically there's a 0 after it, so let's not even worry. Alright, temperature. Remember to go to Kelvin. We had 273.15. Oops. So we're going to have 298 would be our Kelvin value. So if we go ahead and do this, now we have enough information and everything's in the correct units to work with our problem. So it was pi over IRT. I is 1, remember? So we can plug in our values. Liter, atmosphere, Kelvin, mole, times 298. Okay. Let's check our units. Always a good thing to do. Atmospheres will cancel. Kelvin will cancel. So we'll be left with moles per liter. Notice that this is in the denominator as liters per mole, but of course, since it's in the denominator, we would flip it over. So we will end up with moles per liter. So we know we're going to end up with molarity. That's great. So if we go ahead and calculate this, oops. All right, so this divided by 0.08206 divided by 298.15. Doing this, I get something wrong. Oh, no, I don't. It's just a really small number. Okay. 0.00142289, whatever. Let's throw in a bunch of sig figs. Kevin has already done the math for us, which is great, but we'll go ahead and do this. I'm going to just go ahead and make some things a little bit neater here. 142. Looks like we're going to need 3 sig figs with all this nonsense that we have here. So we'll just keep that in mind. So now that we figure out the molarity, what the heck are we going to do? If we look at the other information we're given with the problem, we are given that we have a mass and a volume. So if we can go from mass per volume to moles per volume, that's going to be our molar mass, right? We know that we had some value is going to be our molar mass. So we're going to be able to use that mystery value to go from our 7.68 grams per 10 milliliters into this moles per liter. So if we go ahead and do that, 7.68 milligrams, or let's go ahead and just put this to grams, because that's molar mass units, right? We have 10 milliliters. We know that this mystery value, whatever that is, oops, we're going to have to put that on the bottom, right? This whole thing should equal our moles per liter, right? And so we can go ahead and figure this nonsense out. This is kind of a really precarious way of doing this because we have 1 over x as our thing. So we can go ahead and just rearrange this. I'm going to just put x there because we like x. So doing all this fun stuff, we can multiply both sides by 0.01 liters. Then we can go ahead and try and figure this out. So if we look at that, we can do that first. I mean, I bet you guys know how to do, algebra. So whatever that over x equals 0.000014289. If we were to move x to the other side, we would get x equals 0.00768 grams divided by 0.000014289 moles. Liters would cancel out, right? So in doing all this crazy small number stuff, let's see if I get the same thing as Kevin. 0.123414289. Doing this, I got 537.47. Kevin got 533. There's probably just some rounding things going on in there. So don't round till the very end. That's always our thing that we do. So I would say that this is 537 grams per mole as our molar weight or molecular mass. So yeah, exciting stuff. So this is really just unit conversion. Very, very fun. We all love unit conversion. Let's go ahead and double check. Let's see if we got the right answer here. Beta carotene. Looking at its molar mass, it has a molar mass of 536.888. We got 537, so we're pretty close, right? We are very much within our kind of like room for error with the measurements that we had for this particular experiment. So this is a very good way for us to be able to calculate molar mass of something. How exciting. Any questions on that one? Just algebra here, basically. So just like any other word problem, take what you can, figure out what kind of quantities you're dealing with. In this case, we had we had pressure and temperature and R and all that stuff. Just do whatever you can with the units. Try and make them work out. That's always how all this chemistry stuff works, right? So that's how we would do that one. You'll have similar problems on your homework, of course. How about we do another one? Of course, if you have questions on the first one, throw it out there. We'll go over them. But if not, I will keep on going. All right, here's another one. methyl salicylate. What the hell is that? That's oil of wintergreen. That's that lovely, smelly, not smelly, it's very minty smelling. It's a really nice thing. Wintergreen. We dissolve this in 99 grams of benzene. Not a solvent we would typically use, but because this is a theoretical problem, who cares? If we know the boiling point of benzene is 80.1 degrees Celsius, and we find that the boiling point of the solution is 80.31 degrees Celsius, and we know that the ebullioscopic constant for benzene is 2.53 degrees Celsius per molal, we can figure out the molar mass. We have enough information to figure out what the heck the molar mass is going to be. So, what the heck are we doing here? Well, I see a bunch of boiling points, and I see a KB, which tells us we're dealing with boiling point elevation, right? We really only have 4 options for this stuff, right, for our colligative properties. Remember that delta TB is going to be I times K times the molality. I, again, is going to be 1 for this. We're not really going to be dealing with ionic compounds because, again, those have kind of tricky Van 't Hoff factors, unless we just assume they're going to be the whole numbers. So because this is, again, a molecule, and again, we have benzene as our solvent, our I is going to be 1. So, going back down here, we have 3 components of this solution, or this equation, right? We have a delta TB, which we could just calculate. We have our I is going to be 1. Very often, by the way, for all these things, the I is always going to be 1 because we don't really need to find the molar masses of our ionic compounds. Those are, pretty much easily done because we would know what their components are. So this is typically done for molecular stuff anyway, so I is pretty much always 1. We have KB for us. Next to KB, that's a squiggly M. That is our molality, right? Fancy M. Hard to do cursive when it's just 1 letter, right? All right, so let's go ahead and look at this stuff. What's our delta TB? Remember, that's going to be the kind of like new temperature minus the original one. Indeed, that's what we're going to do. So the molar mass of methyl salicylate is what we're calculating, right? So we already have TB, right? We already know the boiling point of our solution versus the pure solvent. No, don't be sorry. Is going to be 0.21 degrees Celsius. So we do have that. And of course, we do have KB. So with that, normally if we were just figuring out what the change would be, that's how we would do it. But this time we're looking for the molar mass. So we know that delta TB is 0.21 degrees Celsius. We have 1 times 2.53 degrees Celsius per molal. I'll make that parenthesis make more sense. There we go. And then times our molality, which we do not know. I'll just put another X there because that's we know that our unit should be molal, right? So we can figure out what X is going to be. Let's go ahead and do the math. We have 0.21 degrees Celsius divided by 2.53. We know that X is going to be 0.083. And that's going to be molal, right? We already know the unit is molal. But technically we're taking degrees Celsius divided by degrees Celsius times molal. So of course we're going to end up with molal. We know the unit already. So that tells us that we have 0.083 moles of, what was this, methyl salicylate per kilogram of benzene. We know we have, what was our mass of benzene to start with? 99 grams. So if we convert that to kilograms, we know how much the mass of our solvent was. We're able to figure that out. 0.083 times 0.099. That tells us we have this many moles of methyl salicylate, right? Kilograms of benzene will cancel out. Hooray. How many sig figs do we have? Looks like just 2. So we'll keep that in mind. So now we have moles. We have grams. Therefore, we can figure out our molar mass, right? We have both of them. We know that molar mass takes the units of grams per mole. So we can just plug in our grams and moles. You could do this with the last problem too. But again, this is much like kind of the stoichiometry stuff that we're doing. If you can find out moles from anything, you can calculate anything pretty much. So, that's our favorite thing to do in chemistry, right? It's just moles. So worst case of anything, just figure out the moles of something, and hopefully that'll get you the right answer. That typically is the case. So if we do this, 1.25 divided by 0.008217, we end up with 152.12. Looks like with our measurements, we're only going to have 2 sig figs. So because of that kind of crappy measurement we had, we get silly data. Let's go ahead, let's go up on Wikipedia and find out what the molar mass is of methyl salicylate. And lo and behold, it is 152.149. Which is, again, really close to what we got. So even with our kind of rounding that we had to do, we're still pretty close, right? It was 152.149. So you can see this is pretty close to what we calculated here. So nowadays, we do have more advanced instruments that can measure molar mass directly. But they're costly. This is a much cheaper way to figure out molar mass of something you don't know. So it kind of just depends on your lab's budget, basically. We would use technically something called a mass spectrometer to figure out the molar mass of something. But that's analytical chemistry. We don't really do that in Gen Chem. So. Really, again, whenever we're working with these, the answer is just find moles. Once you have moles, you can figure out molar mass because you're given the mass to begin with. So multiple ways to do that there. So yeah, cool. Any questions on those two? So you can see here, kind of just doing a simple experiment is a relatively accurate way of figuring out the molar mass of something. So this has been used pretty widely historically to figure out molar masses of various compounds. So how exciting. So you do have homework problems that are kind of going to be, on this, along these lines. So cool. All right. Well, I think we'll probably have a little bit of time. We can do some more problems towards the end. But let's talk about colloids real quick. We'll get those out of the way. And then we can do some more practice. The homework, by the way, is up on Canvas. It is due this Sunday, so make sure you go ahead and do that. It may seem long, but a lot of the problems are like, choose one of these to be the most accurate statement, or is this true or false? So hopefully some of those shouldn't take too long. Alrighty. Cool. Let's talk about colloids. Ooh, let's use black, though. Colloids are kind of a special case. So we have true solutions, and we have what are called suspensions. True solutions are ones we've talked about. These are always translucent. That means we can see through them. So in other words, that's saying they're clear. But sometimes they're colorful. So they can still be clear but colorful. Like apple juice is clear, though it is kind of that yellow-orange color, or brownish, I guess. That would be a true solution, right? We have completely, homogeneity there, and these behave in ways that we can predict with our kind of things that we've talked about. We can use our colligative properties on them. Suspensions, on the other hand, are going to be something like sand and water. If we were to shake it up, that sand would kind of be floating around in the water, right? But eventually will settle out. You will end up with your sand kind of going to the bottom over time, and you'll end up with your water on top. That's just by density, and things will settle out in a suspension. So these have very, very large particles in them that will settle out over time. And so we're going to see that we kind of have... these are also not clear, by the way, whereas true solutions were. In the middle, though, that's where colloids are going to go. They're kind of in between true solutions and suspensions. Where colloids have properties that they are sometimes clear, but nothing ever settles. In a colloid, in a true colloid. So colloids are kind of in between real solutions and suspensions. So they're just kind of the intermediate ones. Some examples of colloids would be like milk, for example, or a cloud. These are kind of easy ones for us to identify. If we look at a cloud, we can see it is not clear, right? We cannot see through a cloud. And we're going to see that, okay, yeah, it's not going to settle out. A cloud, if you were to somehow encapsulate a cloud or fog or something, it doesn't really settle out. The particles just don't come and go to the bottom. Like clouds stay around until they burn away or they precipitate or something. And the same thing with milk. If we have our milk, it's just going to sit there, that white liquid, it's going to be there, and it's not going to settle out. We're not going to get white solids at the bottom and clear liquid at the top, unless it rots or something or coagulates. But that's technically a suspension then at that point. So we have tons of other colloids. Foams are often colloids. Gels are colloids. These are kind of examples that we have. So again, with your foam, you're not going to settle out your particles, but you're not able to see through it. Gels, though, you typically can see through. For example, Jello, which is going to be a colloid of gelatin and water, we can see through Jello. So sometimes with colloids, you can see through them. The reason that all these happen, by the way, is because with true solutions, we have really small particles. Those are going to be ions or small compounds that are completely dissolved. They're surrounded by water. Everything's happy. With suspensions, we have very large particles. Like that grain of sand, for example, would be huge, right? It's millions and millions of molecules or atoms. And so those are really, really big. And then the colloids, we're going to see that we have intermediate particle size. So these typically go from kind of the nano to, or here, let's just, this is just a complete mess. Let's go ahead and just write this down here. So colloid particles are typically within the nanometer to micrometer range. And that's the diameter if they're roughly spherical. Not something you necessarily need to like memorize, but that's kind of the idea of where these things go. There are some interesting properties here that we have, in that all of these will affect light. They will disperse light. So when light hits these particles, because they are big enough, they can actually reflect light in different directions. So, for example, if you're going through fog is a colloid, if you have your headlights on, you're able to see the path of light as it goes through. If you're just driving around on a clear night, and you've got your headlights on, you just see things illuminated. You don't see really the path of the light. But as soon as you put that fog in there, you begin to see the light as like a beam. You can see the exact path of the light as it goes through, because those particles are reflecting the light in different directions instead of just allowing it to pass through. This would be something also like if you're at a laser show, you have to have the fog machines on. Because lasers, if you just have a laser pointer or whatever, you point it, you can see the dot on the wall, and that's it. But if you have an aerosol there, or a fog or a cloud or something, you can see the laser as it goes from point A to point B. And so, if you think about those spy movies, when they're robbing the museum of its gems or whatever, and, they have those, laser detection things, the spy will always spray something there. They're going to spray an aerosol to make those lights visible so they can see exactly where that path of the laser is, so that they don't trigger the alarm or whatever. You know how movies work. So this is called the Tyndall Effect. Where you can see the path, or the path of light is visible. So I do have a video of this. One sec, let me pick it up for you guys here. Where you can see the Tyndall Effect in action here. So let me just pull that up real quick. Colloids. Where the heck would colloids be? Let's find this for you guys. Of course, if there's any questions, put them up here, but we'll go through them. So, colloids. Is this my colloid video? Nope, that's conductivity. Give me just a sec here. Let's find this video. This is peculiar. That's supersaturation. Aha, colloids. Okay, cool. pop open this. So two seemingly similar solutions, yes? So we're going to see here I have a laser pointer. And I'll be zapping these periodically. So you're going to see the light on the bottom for sure. And then we're going to see in one of these, which is a colloid, that we can see the light beam. So you see the light beam in that one because it is a colloid. You can see the path of the light that it's going through. If we look at the one on the right, however, we can just see the dot at the bottom. We can't see the path of light as it goes through. So light will just go directly through a colloid or through a solution, but through a colloid, we can see the actual beam of light. So you can see exactly what the path of that light is as it goes through that particular colloid. Versus a solution, the light just shows up at the end. You can't see its pathway. And so that's the Tyndall effect. So, think of it as car headlights are laser beams. You need a colloid there. So let's do some examples of colloids. Colloids come in all kind of shapes and I don't want to say shapes because they're all solutions. They don't really have shapes, but all sorts of different flavors, right? So, for example, a colloid that has a solid in a gas. By the way, these are, instead of calling them solute and solvent, we call this a dispersal medium. Instead of a solvent. We can still call this a solute if we want. But we would have the larger component be our dispersal medium, because these aren't really dissolving them necessarily. So for example, a solid in a gas would be something like smoke. So smoke would be a colloid where we have solid particles that are kind of dissolved. I can't say that. They're dispersed in air, which is a gas. And so that would be, for example, soot particles dispersed in air. We could also have a liquid in a gas. What color? Yeah, let's just use that. We have aerosols, which are liquid particles. So something like hairspray or whatever, you have liquid particles that are dispersed throughout a gaseous phase. So fog would be an aerosol. Hairspray. Clouds, for example. Let's see, what else do we have? We could have, what would this be called? Emulsions? Which could be liquids in liquids. This would be something like mayonnaise or milk, where we have particles in there that are liquid generally within other liquids. So if you take oil and water and add an emulsifying agent, like an egg yolk, for example, you can get mayonnaise, right? Which is a liquid in liquid, basically, as a colloid. Foams would also be an example of... Actually, those are going to be gases and liquids instead. I mean, these are just examples. Those would be gases in liquid. That would be like shaving cream. You know what foams are. Let's see, what other fun ones do we have? We have gas and solids as well. These are technically... You could call them foams also. For example, this would be like shaving cream or mousse. For a gas and a solid, that would be something like styrofoam, where you have air particles trapped within a solid, and you get that light, fluffy kind of idea. They're very similar to liquid foams. But you get the idea here. There's tons of different examples. The point is, with all of these things, though, that light is going to be dispersed once you get there. And none of these will settle out over time. So unless you like do weird things to them. So those are our colloids. Let's see, what else do we have? We do have ones that are solid in solid, but those are tougher. That would be something like stained glass, where you have solid particles dispersed in a solid medium. For example, stained glass would be, I think those are called milk sols, but who knows? But stained glass would be another example, where you would have solid gold dispersed in glass, which would be silicon dioxide, some sort of gold thing, whatever it may be. In silicon dioxide, that would be another example of, now this time, a solid in a solid. So your dispersal mediums can be solid sol. Okay, then there you go. There you go. There's our name for those. Again, this is not something you're going to need to memorize, but these are just examples of various colloids that we might have. Of course, you can have solids in liquids. I don't even know how many we have left, but you see you can have all sorts of different like combinations here. So starchy water kind of gives it that cloudy appearance. Like your pasta water will be cloudy afterwards. You can shine your light through it. You would be able to see the beam of light as it goes through. The point is, of all this, you have different ways to do it. They will not settle out, and they are basically kind of intermediate sized particles. Oftentimes, colloids have a high molecular mass. So your proteins and your large macromolecules or various polymers would be colloidal if you were to dissolve them. This is often the case with large molecular weight things. Small molecular weight things often will make solutions, but the larger your molar mass is going to be, the more likely you are to be a colloid. So again, just terminology here, and some kind of physical stuff about them. All right, so there's your colloids. So really, it's kind of like, you'll see like on the homework the types of questions that I would ask about colloids. So it's going to be mostly conceptual stuff, like, of the following, which of these do you think is most likely to, exhibit the Tyndall effect or something? And you'd be able to see, things that you would expect to dissolve fully, like ionic compounds, versus something like starch, where you'd have something really big, or a protein, which would be more likely to reflect light. All right, enough of colloids. They're boring. Let's do some more problems here. Let's do some, what other fun solution stuff shall we do? Let's do some unit conversion. Let's go back to our solution. What is this click to view message nonsense? I don't even see that on my own screen. Oh well. Who cares? Let's do some math here. So remember, for dilute solutions, we're going to assume it has a density of 1. As you can see, this is pretty dilute, 10 to the minus 5. You know, not very much solute at all here. Let's try and figure out let's do some unit conversions. Why not? We're done with solutions, by the way, so we're just going to do a few problems here. We'll start kinetics tomorrow, but we'll just kind of do some practice here. You have homework, you know, you'll have similar stuff in your homework, so yeah. Let's go ahead and do this. Okay, so remember that parts per million is going to be 1 over a million. That's always done as mass. And for so we're basically going to want to figure out how we can convert our solute into grams and our solution into grams as well. Doesn't really matter. For us, we can take any volume we want. We're just doing a unit conversion. We're essentially going from moles per liter to grams over grams. So doesn't really matter what our volume is. We don't really care. We're just going to be converting directly, converting 2 unit conversions or conversion factors. So we know we have 1.062 times 10 to the negative 5 moles for 1 liter. Or for us, that's 1,000 milliliters. Right, that's what molarity is. We know that we're going to be able to use rho here, density, to go from liters to grams. And we know, of course, we have molar mass to go from moles to grams. So let's go ahead and do this. Notice because the solution is a strong electrolyte, it's a nitrate, we know that the molarity of our lead-2 nitrate is the same as the molarity of the lead, because we would expect it to dissolve fully, because it is a strong electrolyte. We can go ahead and look up lead's atomic mass. All right, lead, let's see what your atomic mass is. It is, where are we? Where is atomic mass on this silly thing? Aha, 207.2. We know how to go from mass to moles, or moles to mass, right? That's atomic mass of lead. That will end up giving us grams per milliliter. Grams of solute over milliliters of solution. If we want to go from milliliters of solution to grams of solution, we're going to have to put milliliters on the top, grams on the bottom. Notice these grams are different quantities. We have grams of solute on the top, grams of solution on the bottom. We're going to see, just like any other unit conversion, these, no, that one's not going to cancel. Yeah, that's the atomic mass of lead, exactly, yep. Just 2 unit conversions here, it's not too bad. So, doing this, we're going to see that we end up with 1.062 times 10 to the negative 5 times 207.2. Oops, totally typed that in the wrong box. Doing this, we get 0.0022, essentially. I did have 4 sig figs though, so we'll keep the 4 sig figs. And this we have 1,000 grams. Remember, we want the bottom to be 10 or a million grams, right? So if we multiply this by 1,000. We know that we have, or here, we'll do it this way. Proportion-wise. We know we have 0.0022 grams of lead per 1,000 grams. Let's see what that proportion would be of 1,000,000 grams. Doing so, we're going to see that we end up with 2.2 grams per 1,000,000 grams. And if you were a good chemist, unlike me, you would make sure to label like what bits you have of each one. And so that would be 2.2 ppm. Did I do the math right, Kevin? Should we just multiply by 1,000, right? Keeping our 4 sig figs. So, this would be the ppm value for this particular solution. Awesome. Okay, good. Very exciting. Very, very exciting. Remember also, if you want to think about ppm as milligrams per liter, you could totally have converted it that way as well. You could have taken your moles of lead, converted those to milligrams of lead, and kept the liter of solution at the bottom. That would also have worked. You would still get the same thing as well. Not anymore, because I've made my density, we have 4 sig figs. But yes, technically, if I left it as 3, then yeah. You're right, Kevin. But not anymore, because I have been corrupt and have changed everything. So this would work also. Remember, if you see parts per billion, that's micrograms per liter. That would be another way to do that if you needed to look up parts per billion. Or remember, that's 1 gram over 10 to the 9th grams, and you would just do a proportion that way, just like we did in this problem. So either way would work. You'll have those as your homework. Here, let's see what else. Let's make sure we have all the tools that we have on the homework here. Who cares? Concentrations, we have parts per billion, parts per million. I mean, it's just the same stuff over and over. Our favorite. Whatever. Looks like we have all that we need there. So, yeah. We're done with solutions. Hooray. Let's see here. What else do we want to do? Yeah, we're pretty much done. So, your homework is up. It's on Canvas. How you're going to do that, I guess I can just show you right now. That is a lab simulation. So those are what we're going to do instead of labs. Here, we'll go here. You will have your lab safety stuff. That's in a solution preparation simulation as well. You'll just go through those. It's a simulation. You're going to basically just learn about lab safety. It's going to have you do a couple of things, like you're going to be washing stuff and, using lab equipment and that sort of thing. If we go to our homepage, you will see a little video here that's going to basically just introduce you to what you can do on the simulation. Those are just going to be sent throughout the semester here. So I do have a bunch of them that are going to be kind of activated at various points. We're going to see you have 2 of them that are due this weekend. We don't have too many overall within the entire semester. So those are going to be due. Those are just kind of you do on your own. They're kind of self-explanatory, dare I say. And so we'll go through those. Your homework here, let me go to student view so I can show you exactly what we're doing here. So, I guess I haven't made these visible for us. I'll make that visible for you guys. I can do that right now. But for your homework, as you do it, where's the lovely image? Okay, so you're going to do these problems here. This is the page that has all the questions. Yeah, it's gonna put the grade in for you automatically once you do that. Thankfully, that's self-graded. I don't have to worry about them. However, if you do have like weird problems, I know Kevin had like a problem where something like lagged out or whatever. He was able to fix it. But if you do have problems with them, just send me a message. We'll see what we can do. When you are submitting your homework, you have 3 file type choices. You're going to be showing all your work. You're going to be doing that on your own paper. You're going to be taking a picture of it or scanning it, and you're going to be submitting it here. You'll just choose a file and click submit for whatever. Yeah. The simulation should be easy. It tells you to do these things, and then poof, you get an A. Easy points, right? So lucky us. Okay, so let me go ahead and I'm on the wrong view. Okay. Oh yes, leave. It's mad at me. Okay, let's go ahead and leave student view so I can make these visible for you. Yes, because this is totally not. My bad. So that should be popping up now for you. You should see that. Let me just check the honors one to make sure that's working there as well. Okay, that one at least has it visible. Yeah, cool. Yeah, they're pretty short. Like, they're not even that bad. So once we get to probably the more complicated ones, they'll take a little bit more time. But the ones with safety or whatever are going to be pretty short. So, that's a good question. I don't know. I will look into that. I'm pretty sure I have some way to like mess with that. If so, I'll give you probably 2 attempts, I guess. Yeah, it looks like you can just stop working and come back, but with the number of like tries you get, I can probably mess with that and see. Oh yeah, right now it's set to unlimited attempts. I'm gonna fix that so it'll be like, yeah, let's say 3 attempts. Hopefully it shouldn't take you that long, but yeah, there'll be 3 attempts. So I'll go and fix this in a bit. Yep. So you'll be able to do that in case you have technical trouble or whatever. Just let me know. Alrighty. Well, with that, I will see you all tomorrow, where we will start chemical kinetics. How exciting! Of course, if you do have questions, bring them up, throw them in Discord, or throw them tomorrow in class. We'll deal with them. That's how things work. So, all right. See you tomorrow.